I'm going to assume that everybody is familiar with the complex numbers. So let me just say very briefly what we're going to be doing. C is the complex numbers, and an element of C is written in the form x plus iy. And you have the usual operations of algebra, addition, and multiplication. And the new feature now, of course, is that I is this magical square root of minus 1. And in the context of linear algebra, it's relevant that the following thing is true. You can think of C as a vector space. C is a real vector space. And its dimension is 2, right? And its basis is the real number is 1 and the complex number I. Right? And that just says that any complex number can be written as a linear combination of 1 and I, where it's important that you note that x and y are real now. So this complex number has two real coordinates, and this is the usual picture, of course, where you put the number x plus iy in the xy plane. Okay, so the fact that R has two operations on it, addition and multiplication, and so does C as addition and multiplication. And basically everything that you can, well, most of the things that you can do with the real numbers, you can, with regard to vector spaces, you can do with the complex numbers. And okay, so here's the main definition, which you can probably figure out yourself. It's what a complex vector space is. It's a set V together with two operations where you can add two vectors, and that's vector addition, and there's scalar multiplication, where the only difference now is that you allow Z to be a complex number. You can multiply by any complex scalar, and then all of the rest of the definition of a real vector space applies: associativity, distributive law, the zero, the identity, and so on. The only difference is you allow complex scalars. All right, so let's just do a couple of quick examples. So, for example, if I asked you to do the following calculation, what would you get? Let's see, 1 plus I times I is the first coordinate, and the second coordinate is I plus I. And so by the usual rules, I squared is minus 1, so that's 0 to I. And another example would be, well, we'll do more examples as we go along. So all of the basic stuff of vector spaces is very similar until you get to norms and inner products. And let's look at norms first and see why there's an issue here. So the triangle inequality says that the norm of V plus the norm of W, sorry, should write it in the other order. The norm of V plus W is less than or equal to the norm of V plus the norm of W. This is a triangle inequality in a real vector space. Well, in a real vector space, these are all real numbers, and you know what it means to say one real number is less than another. But what's the norm of a vector in a complex vector space supposed to be? Where V is, let's just say, in Cn, excuse me, it has n coordinates z1 through zn, where these are complex numbers. Well, the obvious thing to try is that what's the norm of V? It's the square root of z1 squared plus dot 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 zn squared. Let me put a big red question mark here. Is this a reasonable definition of norm? And I know you're all clamoring and saying, no, that's ridiculous. Because you can't, there is no decent notion of square root of a complex number. And even if there was, if this was a complex number, the triangle inequality, there's no way the triangle inequality could hold, because it would be some relation involving complex numbers. You'd be saying something like z is less than w plus u. In other words, you'd be saying that one complex number is less than or equal to another. But this is nonsense. There's no such thing. But of course, you can take the absolute value of a complex number and get a real number, and it does make sense to say that the absolute value of one number is less than or equal to the absolute value of another, and because these are real. And so basically that's that tells you what to do, how to fix this problem. The definition is that the norm of a vector v, if it's in Cn, is the, I'll write it as absolute value of z1 squared plus absolute value of zn, excuse me, squared, and then the square root of the whole thing. And this is a real number which is greater than or equal to 0. So even though you're talking about complex numbers, when you start talking about norms, the norms are real so that you can compare them. So let's say, whoops, let's say that again. So we're on Cn, which is the set of n tuples of complex numbers. And I just told you how to define the norm of a vector in Cn. And, well, that's sort of the first version of norm. And when we were doing real norms, we had the abstract notion. So what's the abstract notion of norm? So if V is a complex vector space, then we define a norm is a map from V not to C, but to R. That's a crucial point. And what does it satisfy? It satisfies that the norm of Z times V is equal to the absolute value of Z times the norm of V. And remember that the absolute value of a complex number is the square root of x squared plus y squared, which is just the length in the plane with the usual distance. And so that's the homogeneity condition, and then positivity, and the triangle inequality. And that's the definition of a norm. Well, just like for Rn, there are other norms on Cn. What's the LP norm? You define the norm sub p of a vector v is absolute value of x1 to the p plus absolute value, sorry, not x1, z1. And then the whole thing to the 1 over p. So it's just like for real vector spaces, and the main thing is when you go from real to complex, instead of x1 here, you have the absolute value of z1. If you're doing it over R, this is what you'd have. Over R, you'd have the absolute value also. And you just use the absolute value of a complex number. Okay. Now, what about inner products? Well, we're sort of working backwards here a little bit. We'd like, we'd like if you have an inner product that if you take whatever an inner product is, I haven't decided yet, but that when you take VV, what you get is the norm of V squared. And well, let's do it in Cn with the usual norm. So then the norm of z1 through zn is absolute value of z1 squared plus and so on, absolute value of zn squared. Well, let's just write what the square is. It's this thing. And well, I'll just write it down, and you'll see why this is the right thing to do. The standard norm on Cn, excuse me, the standard inner product on Cn is the following. You define the inner product of z1 through zn, the inner product of that with w1 through wn. You might think that you take zi wi, but you need to change that. What you take is z1 w1 bar plus dot 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 zn wn bar. And the crucial thing here is that you're putting the complex conjugate on the second term here. And remember, the complex conjugate is the thing which takes x plus iy to x minus iy. And it has the nice property that if you have a complex number, the absolute value of z squared can be written as z times z bar. And the point of this is that with this definition, if you take v, what do you get? Well, this is the inner product of z1 through zn with itself. And by definition, that's z1 times z1 bar plus dot 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 zn times zn bar. And so that's just the absolute value of z1 squared plus dot 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 the absolute value of zn squared. And that's what I wanted. That's a real number, and it's the formula that I wanted. That is to say, that's what I took to be the norm of v squared. So you need the bar on the second term. So you don't just get z squared, but you get absolute value of z squared. All right, that's the key point, is you're not getting z1, which is to say z1 squared, which is some complex number. You're getting z1 bar, which is the absolute value of z1 squared, which is what you want. So what's an inner product on a complex vector space? Well, it's the definition that you knew with one little wrinkle. An inner product on a complex vector space is the following. It's written like this, and it takes a pair of numbers a pair of vectors v and w in this complex vector space to a complex number. This is going to be a complex number. And what properties does it satisfy? So it's a map which takes two vectors and from them gives you a complex number, not a real number. This is correct. It's a complex number here, satisfying what conditions? Well, the first one is that it's linear in V. And when I say linear, I mean complex linear, which is to say, if you take z, v, w, what you get is z times v, w. Okay, so this says that if you pull a complex number out of the first argument, it just pulls out front. And so this is a complex number. You're multiplying it by another complex number. Those two sides agree. And of course, it's also additive, which is v plus v prime w is equal to v w plus v prime w. So this says that it's linear in the first variable. That's what these two conditions are. And you might think that you want it to be linear in the second variable, but you don't. It's what's called conjugate linear. In W. And what that means is that if you have something like this, VZW, the Z pulls out just like before, except that it gets a bar here. And I'm even going to make the bar in red. It gets a bar here. And it's also additive. The obvious identity for V1, W1, for V inner product with W1, W2 is the sum. But the crucial thing here is that when you pull the Z out from the second coordinate, it comes out with a bar. And that's forced on you by this formula right here. If you want this to be an example of an inner product, because of this bar on the second term, scalars are going to pull out with a bar. And with that change, a lot of what we were talking about goes through. So let's just finish the statement. So what else? What are the other properties? So before we had, so that's the bilinear property. It's linear in the first variable, conjugate linear in the second. And what about symmetry? So how is VW related to WV. Excuse me, WV. Where you, what happens when you change the order. And if you think about it, this can't possibly be right, but what is true is it's correct with the bar over here. So these are both complex numbers, and they're not equal. Well, the VW and WV aren't equal, they're only equal after you take the bar. And what's positivity? Well, positivity makes good sense now. You define the norm squared of a vector is the inner product of the vector with itself, and you require that this be greater than or equal to 0. This is real, so it makes sense to say that it's greater than or equal to 0, and it's equal to 0 only if the vector was equal to the 0 vector. Okay, and with this definition, the inequalities hold. So the Cauchy-Schwarz inequality says that the absolute value of VW is less than or equal to the norm of V times the norm of W. And the triangle inequality says that the norm of V, the norm of V plus W is less than or equal to the norm of V plus the norm of W. And everything in this, all of these things over here are real numbers. As a matter of fact, positive real numbers. Okay, well, that's a good place to stop. I know nobody's paying attention anyway because you have a test coming up. So that's all for now, and I'll see you in class.